But I first thought I'd ask if anybody has any questions. We do have a test this week, of course. You have a face-to-face test, and you also have an online test due. The online test is due by tomorrow, by Wednesday at midnight. But you'd be crazy if you don't take the online test at least once before taking the face-to-face test. The face-to-face test, the earliest you could have taken it is tomorrow, and the latest you can take it is a week from tomorrow. And I also posted very specific dates and times and locations for times at which I could proctor it via Zoom. You're supposed to email me that information by 11:59 p.m. tomorrow. Let me know exactly where you're and when you plan on taking it. There's also times where you can take it tomorrow. I mean, Wednesday, and that would be Wednesday in person. So you'd have to come to the Virginia Beach campus. It'd probably be in JC 21, but it could also be in JC 12. It could also be in JC 26. So you're just going to have to look for me and figure out where. But the main thing is your times to taking it is at 12:20 or at 12:30 or at 10 till 2 or at 2 p.m. Those are the times you can take it on Wednesday. And that's with me personally doing it. If you have a laptop computer you can bring with you, that might be helpful because I find it a little easier for my online students to take their test on using the test version that's actually on their computer. Even though it's going to be the same test, whether you take it on paper or whatever, it's just a little easier for me doing the internet students via online. So otherwise, I have to make copies for everybody and turn them into the testing center, and that's kind of a pain. So, anybody have any questions before we get started? Okay. Well, last time we actually more or less completed chapter 8. I showed you enough examples of what I was most concerned about, but in retrospect, I decided there's probably a couple more things I want to talk to you about because I hinted at it using the new potential energy function for Newton's law of gravity as opposed to the weight equals mg. When you use that form of gravity, weight equals mg, that is a conservative force, and it ends up giving you a potential energy function that's U equals m times g times y, where wherever you set y equals 0 is arbitrary. But when you use Newton's law of gravity, F equals negative g m over r squared r hat, and you get a potential energy. Potential energy becomes up. It turns out to be negative. It's negative g m over r. And that's the only time if you're using my version of conservation of energy, the one that says UI plus KI plus work in equals U out plus, or excuse me, equals U final plus K final plus work out plus E loss. And using that idea of a way to work it, the U equals negative GMM over R is the only time you automatically put in a negative sign. Okay. You might actually get a result that gives you a height that's negative. That's certainly reasonable using my paradigm. But the main thing is none of the quantities that you put in should be negative. But you might solve for a variable like X that would turn out to be negative. So with that in mind, I want to go ahead and show you those things. And I wanted to just remind you exactly what power is so that you can work from here on out on power problems. The big thing to remember about power on average is the energy used, absorbed, consumed, whatever per time. That's on average. That energy can be potential energy, that energy can be kinetic energy, that energy can be work, that all sorts of stuff. If you want the instantaneous power, then it's the time rate of change, i.e., the derivative of some form of energy with respect to time. So du over dt would be the power when you're thinking about the energy being potential energy. If you're thinking about the energy just being E, then power is dE dt. If you think about power being work divided by time, then power is equal to dW dt, and you can replace dW with F dot dL, and that's another derivation that I wanted to give you. So let's go ahead. I'm going to share my iPad screen with you folks. It seems like no one had any questions, so I'm going to press on. So we're looking at some of the numbers for example 8 8:12, and I'm going to go ahead and read the problem to you so you'll know exactly what we're talking about. It says, example 8:12, package dropped from a high package dropped from a high-speed rocket. A box of mass lowercase m is allowed to fall from a rocket traveling outward from Earth at a speed of 1,800 meters per second when 1,600 kilometers above the Earth's surface. The box eventually falls to Earth. Estimate its speed just before impact and ignore air resistance. So that's a typical type of problem where we can actually make use of the Newton's second law, or excuse me, the Newton's law of gravity version of potential energy. So that's what I'm going to do here. So I'll write down solution, and this solution has U initial plus K initial plus work in is equal to U final plus K final plus work out, excuse me, plus E loss. In this case, we're ignoring air resistance. I'm not imagining compressing any springs or anything like that. I basically am just looking at an object that has some initial potential and kinetic energy. Specifically, the rocket ship will be moving at 1,800 meters per second at 1,600 kilometers above the Earth's surface. At that point, I have both the kinetic energy associated with the package moving the same speed as the rocket ship at 1,800 meters per second, and I have potential energy for the rocket ship and the package being at 1,600 kilometers above the Earth. And then when it lands, I have the kinetic energy that allows me to find the velocity just before it hits the Earth. But I also have a potential energy associated with being it being at an elevation equal to the radiation of the, or excuse me, equal to the radius of the Earth's surface. So that's what I'm going to go with. So far, that means I can get rid of work in, I can get rid of work out, and I can get rid of E loss. And now all I have is U initial, which is G times M for the mass of the Earth, times lowercase m for the mass of the package, over R initial, plus 1 half mv initial squared, plus 0 is equal to negative G m m over R final, plus 1 half mv final squared, plus 0 plus 0. So you can now see that I can basically multiply by 1 over lowercase m. And of course, whatever I do to one side, I have to do to the other. But when I do that, that's going to get rid of this m and this m. And this m and this m is going to be gotten rid of as well. And now I have negative g mass of the Earth over r I plus 1 half VI squared is equal to negative GM mass of the Earth over R final plus 1 half V final squared. So now what I'm going to do is go ahead and plug in my information. So I have negative 6.67 times 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times the mass of the Earth. And I don't even think I actually am going to need that, but let me see. Oh, yeah, I guess I will need it. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And then the initial height is not the 1,600 kilometers, it's the 1,600 kilometers plus the radius of the Earth. So the 1,600 kilometers is 1.6 times 10 to the sixth meters. So that's the actual height, but that height has to be added to the radius of the Earth, and the radius of the Earth is 6.38 times 10 to the sixth meters. meters like that. So that gives me the total height initially plus 1/2. Now the initial velocity is 1800 meters per second. That's going to be squared. That's equal to, again, negative 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th. I'm going to leave the units off this time because it's so hard to fit everything in. And this time it's just going to be at an elevation that is the radius of the Earth. So that's 6.38 times 10 to the 6 meters. And then plus 1/2 V final squared. And the V final squared is what we're looking for here. So what I'm going to do is try to compute that first big fraction. So 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th. Now I'm going to divide that by parentheses 1.6 times 10 to the 6th plus 6.38 times 10 to the 6th. And that all looks good to me. Just making sure my figures all look good. 7.98. Yep. Yep. Okay. So when I do this computation, whoa, Nelly, I just erased everything. That's not helpful at all. 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by parentheses 1.6 times 10 to the 6 plus uh, 6.38 times 10 to the 6 close parentheses equals. This gives me negative 4.998 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. And those units turn out to be Newton meter squared times a kilogram, Newton meter squared per kilogram squared times a kilogram is going to give me a Newton meter squared per kilogram. Then I'm dividing it by a meter. So this is a Newton meter per kilogram. So it's a joule per kilogram, basically. That's another way of looking at it. Now, in the case of the zero point 0.5 times 1800 squared, that gives me 1.62 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6th. And that should be in meters squared per second squared, which should be the same units as joules per kilogram. Let's check that. Newton meter per kilogram is equal to a kilogram meter per second squared times the meter that was already there and then divided by the kilogram that was already there. So that cancels that out, and you see that is equal to meters squared per second squared. So we're good on that. That's going to be equal to this other figure, which again is a negative number. And I'm going to try to separate these a little bit because I had to use an extra line here. So I just want to make sure it doesn't get convoluted with the last line. So 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th. And now I'm going to divide that just by the radius of the Earth, which is 6.38 times 10 to the 6th. And that gives me negative 6.252 times 10 to the 1, 2, 3, 4, well, 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th joules per kilogram again, plus 1/2 V final squared. So if I pull the 6.5252 to the left, then we can get a little bit more headway. So I'm boxing that off too. So I'm going to take the negative 4.998 times 10 to the 7th 4.998 times 10 to the seventh. I'm going to, that's a negative, so I'm going to add a positive quantity of 6.252 times 10 to the seventh. And that gives me 1 point, ooh, I still want that in blue. That gives me 1.254 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the seventh joules per kilogram. And of course, that's just taking into account this term and this term, but I still have the plus 1.62 times 10 to the 6 joules per kilogram. And then I still have the 1/2 V final squared. So I should be able to solve for V final by taking the 1.254 times 10 to the seventh and adding to it 1.62 times 10 to the sixth. And that gives me the square root of 2 times 1.416 times 10 to the, I suspect that's 7, 1, 2, 3, 4, 5, 6, 7 times 10 to the seventh meters squared per second squared. Remember, we did find that joules per kilogram is the same as meters squared per second squared, but now since we're taking the square root, we see that, oh, that would be a much more convenient unit to use. So that's why I decided to use that instead of the joules per kilogram. Because when you take the square root of meters squared per second squared, clearly you get meters per second. So now I'm going to take that number and multiply it by 2. And now I'm going to take the square root of all that, and that's going to give me the velocity. And that gives me 5,322 meters per second. So if you were to drop a package out of a rocket ship when it's flying away from the Earth at 1,800 meters per second and is at an elevation of 1,600 kilometers above the Earth's surface, when it lands, if we ignore air resistance, it will be traveling at 5,322 meters per second just as it hits the Earth. So that is an example that I wanted you to see worked. Another thing I would like to see, let you see, is there's a kind of a neat little happenstance that occurs when you're using this form of potential energy. Specifically, if you imagine what kind of velocity would you have to fire a projectile at from the surface of the Earth to have it completely escape? So we're imagining shooting like a ball or a rocket ship out of a big cannon or something like that from the Earth's surface. Shoot that out with such a velocity that obviously, as soon as it takes off, the Earth's gravity is going to start slowing it down, slowing it down, slowing it down, and it's going to continue slowing it down until, and here's the idea that we're going, theoretically what we're thinking is it'll just have enough kinetic energy initially such that when it reaches infinitely far away it'll have zero kinetic energy. So that's like the slowest speed you could have to actually escape a planet's gravity well. So we call that the escape velocity. Using that idea, we can now set that up and calculate exactly what that escape velocity would be. And that's what I'm going to do. And then I'll show you one more example with it that's kind of interesting. So again, at, whoa, at what velocity might a projectile be fired? Ooh, so that it leaves Earth, leaves the Earth's surface, and reaches r approaching infinity as v approaches zero. So using our equation, U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Again, we're going to go on the same assumptions that we did before. We're ignoring air resistance. We're not allowing any springs to be compressed or anything like that. But what I am going to do is I'm going to say the initial potential energy is negative G times the mass of the Earth times the mass of the projectile divided by the radius of the Earth. Now, we're assuming that it has enough kinetic energy that it escapes, so this velocity will be considered v escape. So I write this as 1 half mv ESC squared. And now, when it gets infinitely far away, we know the potential energy is going to be zero. And by design, I just said I wanted to imagine what the initial velocity would be that would result in the object reaching infinitely far away at the same time that it brings its velocity down to zero. So that would mean the kinetic energy is also zero. So from this, I can get that for starters, I can multiply both sides of the equation by 1 over m. And one side of the equation, of course, is just zero. But I can do that. And then, in addition to multiplying by 1 over m, I can then solve for v escape. And what I'll get is v escape is actually equal to the square root of 2 times g times the mass of the Earth over r for the Earth, like that. And that is the actual formula. So that's the formula for escape velocity. And that's kind of a neat little scenario, but you can calculate that, and it is escape velocity. It's on the order of several thousand meters per second, or kilometers per second is really the escape velocity's normal unit. Uh, in fact, I was looking. I was going to pull out a figure. I figured your book probably calculated it somewhere, but I don't see the number off the top of my head, and I hadn't prepared to do that myself. But either way, we could we could do it just by using what we just found out. So let me go ahead and calculate this real quick. I'm going to say 2 times 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th. That's the actual mass of the Earth. So I've got 2 times g times the mass of the Earth. Now I'm going to divide that by the radius of the Earth. And the radius of the Earth is 6.38 times 10 to the 6. So I'm dividing 7.97 times 10 to the 14th by 6.38 times 10 to the 6th. That gives me 1.25 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And now I'm going to take the square root of that. Oh, yeah. Now I'm going to take the square root of that, and that'll give me the escape velocity. And, ooh, it's even bigger than I remembered. So the escape velocity, V escape, is equal to 1.12 times 10 to the fourth meters per second. So we're talking around 11 kilometers per second is the escape velocity for the Earth. Any questions on that? Now, with that problem in mind, this is where I'm going to bring up the next part. What if we tried to figure out what would be the radius of a planet, or what would be the radius of the Earth, for instance, if we wanted to assume it behaved like a black hole? And by that, I mean, imagine a particle taking off from the surface of the Earth at this new radius with a fixed speed such that it just reaches infinitely far away at the same time as velocity reaches zero. if we find that radius, then what we found is the radius that the Earth would need to be in order to behave like a black hole. So that's a kind of neat calculation we can do. And it's interesting because it gives us exactly the right result, even though the right result should come from general relativity. And we're not using general relativity, we're using classical physics. So let's do that. What is the radius? Oops, I went an extra little hump there on my word radius. So, what is the radius of the Earth if it behaved like a black hole? Now, a black hole was hypothesized to be an object that was so gravitationally strong that not even light can escape it. What we're doing is looking on the edge of that, just saying this is the area where light can just barely escape it. So this is sort of the if I took away a single milligram of it, it would then be, or if I added a single milligram of mass to it, or I took off a single millimeter of radius from it, then it would be a true black hole. So we're using that as the sort of the turning point. So now if I use my equation for conservation of energy, UI plus KI plus work in equals U final plus K final plus work out plus E loss. Again, I'm making the same assumptions as we did on the last couple of examples. All of this stuff is going to be zero. And in fact, just like I did last time, I'm going to assume that its potential energy reaches zero at r approaching infinity and that its kinetic energy reaches zero at r approaching infinity. So these two are zero as well. Now I can plug in the data. I'll say negative g. I'm not going to subscript this Earth this time because it will actually be true for any planet. And the other one too, by the way, the 2gm over r. If you put in the mass of any planet for that m and the radius of any planet for that r, then you'll get the escape velocity for that planet. If you do it for the Earth, then you're just getting the escape velocity for the Earth. So the same thing's going to happen here, except this time I'm not going to write it like I'm working for the Earth. So I'm going to say m times little m over the radius of the planet, which I'm going to call big R, plus 1/2 little m. And now in place of velocity, I'm going to put c, the speed of light, and all that's equal to zero. So what we're trying to solve for really is the r. I can pull the g m over r to one side and put the 1/2 mc squared on the other. The m's cancel out like we expect, and lo and behold, I get r is equal to 2gm over c squared. And this is what we call the Schwarzschild, and I'm probably going to horribly misspell this. Scharz. Mm, yeah, there's a lot of stuff. Schwarzschild, SCH. I can't. Oh, actually, I think there's a W that's before that. That's the Schwarzschild radius, and I'm not even going to try to spell it because I just realized how long it's been since I actually looked up that word. But it was named after the person that came up with the first solution to Einstein's equations, a guy with the last name of Schwarzschild. And in fact, I think he even died shortly thereafter because he was unfortunately at battle in World War One. So it was weird. Einstein made his publication of the special theory or the general theory of relativity and then said, these equations are complicated. It might be, centuries before anybody finds a solution. And like literally a guy had a solution in the same day just by using a lot of symmetry and stuff like that. But the neat thing about this is this is the radius of the event horizon. So this is the radius of the event horizon of a black hole. Now, the event horizon is basically the point at which there's no return. So once you actually move in towards a black hole and you get to its event horizon, everything's done then. You don't have any choice. You're going to be spaghettified. The part of your body that's closest, or the part of your ship or whatever that's closest to the black hole, will be pulled at such a higher force than the other end of the spacecraft that it'll be stretched really, really long and compressed perpendicular to that. But it turns out this formula is the absolute correct formula from general relativity, even though we did it without general relativity. So if you wanted to know the radius of the Earth as a black hole, we could write EBH for the radius. And now I can calculate all this. So I'm going to take 2 times 6.67 times 10 to the negative 11th times 10 to the negative 11th times the mass of the Earth, which is 5.98 times 10 to the 24th. And then I'm going to divide it by the square of the speed of light. So I'm going to say uh, 299,792,458 squared, close parentheses, and this gives me 0.00888 meters, which is 8.9 millimeters. So the Earth, if you wanted it to be a black hole, you would have to compress it such that, and of course I grabbed the only ruler that doesn't have a centimeter scale. Uh, you'd have to compress it to a size about that big, the distance between my two thumbs there. That's about how big the Earth would have to be in radius. If you wanted it in diameter, you could jump all the way up to say uh, maybe 1.6, something like that. So the diameter of it would be about this big. So uh, on the order of basically 1.8 centimeters. Yes, Michelle.
Oh, sorry. Didn't hit my button the right
Let
way.
me check my
Um,
chat. She might be typing.
oh, can you hear me? Is it working?
Did you have a question, Michelle?
Yeah. Can you
Oh,
hear me?
I hear you a little bit, but it's very, very quiet. Or I'm
Oh,
hearing
okay.
things and it's not quiet at all. Oh, now
Um,
I got you. Okay, the volume
okay.
had been
I
turned
was
down.
like, I don't want to be yelling.
No problem.
Um, with the C value in this,
Hmm.
can you remind me what that is indicating?
Gotcha. Yeah, that's actually really important because we don't talk about that much in this course. And now, if I can find my Apple Pencil, where the heck did it go? Oh, there it is. Okay. Yes, c is the speed of light, and we decided to define our unit of time and distance in such a way that the speed of light is actually a fixed amount, and that is 299,792,458.0 with an infinite number of zeros after it meters per second. That's what the speed of light in a vacuum is. Now, that's probably not that helpful because it's nearly 300 million, but you could say it's approximately 3.0 times 10 to the eighth meters per second. So that's 300 million meters per second. Again, not very clear, but to give you some idea, that's 186,000 miles in a single second. Or another way of thinking about it is it's enough time, or it's so fast that it could go around our equator 8 times in a single second.
That's crazy.
Yeah, so it's really, really fast. It's the fastest thing that we know of. We believe that nothing should ever go faster, and the only things that can go that fast are the things that have zero mass. So that just gives you a rundown of it. But what we did do is we found out that if we wanted to make Earth a black hole, it could be a black hole, but it would have to have a diameter of about 1.8 centimeters. So very, very small.
Is like when you talk about the speed of light, is that measuring like the electron of the light?
Ah,
Mm.
yeah. So that's a very good question. So it turns out, uh, Newton worked out a lot of physics about optics, and he ended up writing like 500,000 words on optics, and it was really a big monumental thing. But he did all of that work and got the exact same equations that we use in this day for optics. And what he found, for instance, was all found by assuming that light was made up of these little particles. We now treat those particles as what we call photons because there turns out to be a particle that has zero mass and it's called a photon. And that's one way we can picture light. Now, after Newton, a bunch of people got figured out that light was very much a wave. Huygens is one of the people, Thomson's another person. But what they discovered was that when you send light, like if you try to pinch your fingers really close to each other, like this, where your fingerprint of your index finger and your thumbprint are almost touching. When you look at a light source like that, what you'll see is repeat traces of your fingerprint and your thumbprint. So you'll see these little lines right close to each other. What's happening there is every little spot between your fingerprint and your thumbprint is acting like a separate source of light. And there, obviously there's an infinity of them because a single point source has no physical dimension, so it takes an infinite number of them to span that whole distance. But when they interact with each other, the troughs can line up with the troughs and you get a really dark spot, or the crest can line up with the crest and you get a really bright spot. That's what's happening between your fingers when you see that extra drawing of your fingerprint curved down like that one, or your extra thumbprint curved up like that one. You're actually seeing a second image. So that's some of the proof that light behaves as a wave, because when it gets in a hole, it shines out from every point in that hole as if each point's a separate piece of light. When that happens, the individual crests and troughs can line up. And if the crest lines up with a trough, you get nothing. And when a trough lines up with a trough, you get bright light. Or when a crest lines up with a crest, you get bright light. But when a crest lines up with a trough, everything disappears. That only happens with waves. So in that intervening period after Newton did all that work, we discovered that light was a wave. And then all the scientists said, well, we've never seen waves except for waves that travel in material, like ocean waves and sound waves and stuff like that. So they said, oh, well, outer space, which we sort of thought was a vacuum, must not be a vacuum. It must have an ether. So they imagined an ether that surrounded everything. And then they, of course, were being good scientists and went out and tried to measure the ether. And it turns out the ether didn't exist. So, uh, but anyways, the result of all that was that we reached the conclusion that Newton was able to do everything he did, treating light as a particle. But since then, everybody got smart enough to realize that that must have just been a lucky guess or whatever. It just happened to work out that way, because later a guy named James Clerk Maxwell comes along, puts together four equations, or more or less derives four equations from all the experiments done in the past, and they're called Maxwell's equations. And if you put them together in just the right way, it tells you exactly what light is. And that's what Maxwell did. He put these equations together and he got what's called a wave equation. It's a very specific type of differential equation that just, when we see it as a physicist or an engineer with training or whatever, we know immediately, oh, that's a wave equation. Well, that's what he did. He said, oh, wow, this is a wave equation. But in a wave equation, you got a very specific spot for the wave velocity. And in that spot for the wave velocity was a constant called the permittivity of free space and another constant called the permeability of free space. And those two are totally unrelated constants. One's about magnetism, one's about electric forces, and they're far different numbers. One's 4 pi times 10 to the negative seventh, the other one's 8.85 times 10 to the negative 12th, all this weird stuff. But it turns out if you take and multiply those two quantities, flip them over, take the square root of that, you get the speed of light. And what he did was that he got this equation. He said, oh my gosh, this velocity, I didn't know it, but this is exactly the speed of light that we recently determined through various experiments. And he, right then, was the only person on planet Earth that knew what light was. So, what is light? Light is an electric field that oscillates in one plane, let's say up and down. That would be called vertically polarized light. And then a magnetic field that oscillates left and right. So, they're doing this constantly, but they also travel in a third perpendicular direction straight out. So it makes this little right hand rule where, for instance, uh, this is the electric field, this is the magnetic field, and this is the velocity. So if the electric field's pointing up and the magnetic field's pointing right, then the wave will be traveling forward. If, on the other hand, the electric field is pointing up and the magnetic field is pointing to the left, then it's traveling this way. So that's what's actually moving is a wave. But in the early 1900s, we were pretty much reaching the point where we decided that physics was all worked out. We're just going to do a few experiments to, make sure that our physics is right to 5 decimal places instead of four or something. And then three experiments that couldn't be explained came up, and that made us discover quantum mechanics. And now the interpretation is both of your answers that you said are right. Light is a particle sometimes, and light is a wave sometimes, and you don't know what you're going to get until you've done the experiment that you're trying to do to determine whatever you're trying to determine. So every time you go to measure light, it could come up acting like a particle or it could come up acting like a wave, and you really don't know until you've done this same experiment before. So I'm sorry I couldn't give you a shorter answer, but I gave you
No,
an
that's
answer.
that's super interesting. I know in the surgical field they have lights now that like don't cast shadows, and I'm sure that that's going into that.
Yeah, there's a lot of neat things going on in the medical fields right now, and actually, we use quantum mechanics, electricity and magnetism, all that stuff to examine even X-rays and CTs and all that good stuff. So, yep, I would not be surprised to find that that's related. Speaking of which, did your homework assignment ever update grade-wise? Weren't you the person that
I need
said
to
you?
look at it. I didn't I can check it really quick.
Yeah, just let me know. I'm just curious if what I did took care of it. I think it should, but if it didn't, it's okay. You just gotta let me know.
Okay,
All
thank
right.
you.
One more thing I wanted to show you about chapter 8 before moving on, and it's just a definition that you're going to need to use over and over and over again this semester and next. And it's specifically power. The average power is some energy. So I'll put a bar over it to represent power over time. So if you talk about a lawnmower engine putting out 4,000 joules of energy every second, which it can't, but just pretend for a second. If you said a lawnmower engine was putting out 4,000 joules of energy every second, the average power would be 4,000 joules per second, which is 4,000 watts. A joule per second is defined as a watt. So 1 watt, which is equal to one capital W, is defined to be 1 joule per second. So when we say something has a power of 4,000 watts, that could mean that it would burn 4,000 joules in a single second, or it could mean that it produced 4,000 joules in a single second, or it could mean that it does 8,000 joules in 2 seconds, or it could do 16,000 joules in 4 seconds, or whatever. But that's the main thing is power is work divided by time or energy divided by time or so on and so forth. So if you want to make this not an average, then you could say power is du dt or de dt or dw dt. In other words, all the different ways you can think about work being or energy being transformed into something, as long as it starts off as energy or ends as energy, then that is a energy per unit time. So all of these are fair game. With that being said, we know work is equal to the integral of F dot dl. So we can go ahead and say power is, instead of dl, I'm going to say F dot dl, all that over dt like this. Well, I'm going to separate that out and call it F dot dl dt. Can anybody tell me what you suspect dl dt is? I saw your answer, Michelle. Thanks. So think of the units. L is a length and T is a time. So what units does dl dt have?
Meters per second.
Exactly. And what does that sound like? What else has units of meters per second?
Velocity.
Exactly. And it turns out that the power is in fact the force dotted with the velocity vector. So that's another equation you can use. A typical problem for using this would be something like uh, a car is riding at 30 meters per second and uses 500 watts of power. Uh, what is the force the engine of the car must be supplying? Well, in that case, the force the engine supplying is directly parallel to the velocity. So F dot V is just F times V. And therefore, you can say, oh, well, the force will be the power divided by the velocity. So if you take the 500 watts and divide it by the 30 meters per second, you'll end up getting what, 50 divided by 3, which is about 66.7. So 66.7 newtons is the amount of force that a car would have to be able to exert on its surroundings to be moving at 30 meters per second with 500 watts of power. Any questions on that? All right. So now I've finished the last little bits of chapter 8 that I wanted to finish. So I need to go into, and I don't know what y'all are seeing right now because I just got a new operating system on my computer and I hit a button and everything disappeared. So, yay me. All right. We're going now to chapter 9, which is called linear momentum. Okay. So that's chapter 9, linear momentum. And you'll notice the sections of chapter 9 are 9:1 momentum and its relation to force. We're going to discuss that. 9:2 conservation of momentum. 9:3 collisions and impulse. 9:4 conservation of energy and momentum in collisions. 9:5 elastic collisions in one dimension. 9.6 inelastic collisions, 9.7 collisions in two or three dimensions, 9.8 center of mass, 9.9 center of mass and translational motion, and then finally 9.10 is systems of variable mass, rocket propulsion. I will tell you that that section 910 is very interesting. And if you're interested in aeronautical engineering, I would say read that pretty thoroughly and understand it. I'm completely skipping that as a section far as covering it and as far as assigning it on test problems. There will be no testing questions on that. That being said, I've tried to get rid of it in the homeworks and I've tried to get rid of it in the practice test, but there still may be a few of them. Just know that you're not going to be tested on it. So by all means, work them, learn how to do them as what you want, but just know you're not going to be tested on it. I will tell you that momentum conservation uh, is something that is another physical principle, but just like Newton's first law and Newton's second law and Newton's third law, this is something you should commit to memory because I've got a whole chapter called linear momentum. It probably would be reasonable to assume that someone might ask you, under what conditions is momentum conserved? Or please state the law of conservation of linear momentum or something like that. But in addition to that, I'll tell you that whatever problem you can solve with conservation of momentum, you can also solve with the center of mass. So that's why we're covering the center of mass in addition to conservation of momentum, in addition to linear momentum. So what is linear momentum? Well, momentum is a vector quantity. We use the symbol P for it. And at least classically, when you learn about relativity, you'll find there's a different formula for momentum and there's a different formula for kinetic energy. We're not worried about that because we're not covering relativity right now. But I'm just telling you, when you get into the realm where things are moving comparable to 1 or 2 to 10% of the speed of light, then these equations don't work. But momentum of a single particle is the mass of the particle times its velocity. And of course, that should tell you that's a vector quantity, and momentum is a vector quantity. If you're wanting to apply, for instance, this to a system or a collection of bodies, then you can say momentum of the system is m1 v1 plus m2 v2 plus m3 v3 plus dot 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 on up to mn vn. Okay, so you can do that as well because all of this comes from Newton's second law, which oddly enough was not given to us in the way that we taught it to you. So what we taught was the summation of the forces is equal to mass times acceleration. And we've been largely using it that way because the acceleration for many of the problems we've been working out has been a constant. But even at this point, writing it as A is a little misleading. Uh, we should probably, just for completeness, remind you that it's the summation of the forces is equal to mass times d2r over dt squared, where r is the position vector. You could call it x vector if you wanted. That would be fine as well. But the fact that we're taking the first derivative of the position vector, that would mean it's the velocity. But in this case, we're taking the second derivative. So we're taking the derivative of it once. That makes it the velocity. Taking the derivative of a second time, that's the derivative of the velocity. So that makes it the acceleration. So this is Newton's second law as we've been discussing it, as the summation of forces is equal to m times d2r over dt squared. But what Newton actually said, and I'll just remind you, this is Newton's second law, sort of. It turns out that that version of Newton's second law is not true all the time. If you have a changing mass instead of a fixed mass, then m d2r over dt squared will not work. What Newton actually said is this. So what Newton actually gave us is the total force, the sum of all the forces acting on the system, is actually equal to d by dt of mv, which now that you've learned what P is, you can say, oh, this means the summation of the forces is equal to dP dt, and that is exactly correct. I'm sorry for the way I wrote it at two different heights on this version on the left here, and it's driving me crazy that I did that. But anyways, that's the version that Newton actually gave us. Okay, so strictly speaking, when you take the summation of the forces equals something, it's technically equal to d by dt of m times v, and that's a product, so you have to use the product rule. So it turns out to be dm over dt times v plus m times dv dt. Notice this part right here is what we've been using for the right hand side, and that's not necessarily correct. As we can see, that's not necessarily correct because we might have a changing mass, and by not having the dm dt times v term, we were wrong. All right, now that we have that, I want to tell you something else. Uh, if the total force is equal to 0, then the summation forces is equal to dp dt becomes 0 is equal to dp dt? And under what circumstances is a derivative equal to 0? Anybody recall?
When it's a constant.
Exactly. So in order for this to actually be 0, then the momentum P must be a constant. So I write these three dots in a triangle means therefore, more or less. So you can say that P is equal to a constant. Now it's still a vector, so I should write it as P is equal to a constant with a little arrow over top of it like that, but that's what it is. And what we mean by that is you can calculate the momentum before some event, and that would be called the initial momentum, and then you can calculate the momentum after the event, that would be called the final momentum. And since momentum is a constant because the summation of the forces is equal to 0, then you can reach the conclusion that P initial is equal to P final. So that's what conservation of momentum is. Of momentum. So conservation of momentum only is true when the total force acting on the system is 0. That being said, if the total force acting on the system is really small compared to all the other forces acting on it, then sometimes you can pretend it's going to be is going to be a conservation of momentum problem, and you can solve it accordingly, and then you can go back and try to look for changes or perturbations to the system so that you could get a more accurate answer, taking into account that it wasn't perfectly elastic. But the main thing is to understand that the main thing to understand is that collisions are things conserve linear momentum when the total force is 0 or the total force acting on it is really, really close to 0. Any questions on that? All right, so that was me giving you a lot of the background on it. I will tell you that with this version of Newton's second law, the summation of the forces is equal to, actually, let me put the little bit more of a gap in that space, is equal to dp dt. If I multiply both sides by dt and then integrated both sides, then what we would get is the integral of the total force over time is equal to a quantity we call J, the impulse. But as you see, the left-hand side is equal to that. So that means the right-hand side is also equal to that. So the integral of dp, which is just change in momentum, is also the impulse. So basically, I've now given you a new concept, a concept called impulse. And impulse is either the integral of the force, in this case, specifically the total force, but you could also calculate the impulse of a force, in which case the impulse would just be the integral of whatever force you're doing times dt. That's the impulse of that force. You could also say, oh, I'm using Newton's second law, in which case I'm calculating the impulse of the net force, and you'd have this as well. But because it's equal to the change in momentum, the impulse is both the change in momentum, P final minus P initial, and it's equal to the integral of f dt. And of course, that means it's also equal to the area under the curve, just like when we learned work was equal to the integral of f dot dl, and we made a plot of force versus displacement like this. The area under the curve is the work from A to B is equal to that area. So that is what we found out in work. And now what we've also found out is that if you make a plot of the force as a function of time, that area is equal to the impulse. Okay, so don't forget that the area under a force versus displacement curve is the work done, and the area under a force versus time curve is the impulse. Now I'm going to go ahead and do a couple of examples so we can see how that works. Actually, before I do, let me remind you of something, or at least point it out. So momentum in units is equal to the unit or dimension of mass times the unit or dimension of velocity. And the unit of mass is the kilogram, and the unit of velocity is meters per second. So the unit of momentum is either a kilogram meter per second, but you can also realize that a newton is a kilogram meter per second squared. So this is the same thing as a newton times a second. Similarly, the impulse J is the units of F dt, which means it's the units of the force times the units of that was supposed to be a T, times the unit of time, which turns out to be a Newton times a second, just like we found out before. So that's another reminder. Oh yeah, the reason why the Newton second is the unit of impulse is because the impulse is also equal to the change in momentum. All right, let's look at example 9.1. It says for a top player, a tennis ball may leave the racket on the serve with a speed of 55 meters per second, about 120 miles per hour. If the ball has a mass of 0.060 kilograms and is in contact with the racket for about 4 milliseconds, estimate the average force on the ball. Would this force be large enough to lift a 70 kilogram person? So what we have here is a mass equal to 0.060 kilograms. We have a initial velocity, which is zero, because what we're imagining here is Roger Federer, in this particular picture, is tossing the ball up. And in principle, the ball could be drifting a little into the court or a little to the right or a little to the left or a little out of the court. But that velocity is going to be so small compared to the 120 miles per hour or so that it's really not that much of a inconvenience or difference. So we're going to assume the initial velocity is zero, and then he's going to hit it for a short period of time, like 4 milliseconds, and it's going to leave the strings of the racket going at 55 meters per second. So V final is equal to 55 meters per second. And what they want to calculate is estimate the average force. So F, and actually I put an arrow over that because it's a vector, but I'm really just talking about one-dimensional motion. So I'm just going to put a bar over it, and the bar represents average, of course. Now, what we know is Newton's second law says the summation of forces is equal to dp dt. Now, the force that you're hitting this tennis ball with is huge compared to every other force this tennis ball is reacting with. So we don't have to use the total force. We can just use the force that the racket is acting, that it's applying to it, and that's plenty because all the other forces are infinitesimal compared to it. So, with that in mind, we can go ahead and try to figure out what the change in momentum will be, and therefore what the force will be. So, what we know also is that delta t, the amount of time it's in contact, is 4 times 10 to the negative third seconds. So the F average is approximately equal to delta P over delta t. And remember, delta always means final minus initial. So we could write this as mv final minus mv initial over delta t. But why write the m twice? We'll just write it as m times v final minus v initial over delta t. And with that, I get 0.060 kilograms. The final velocity is 55 meters per second minus the initial velocity is 0 meters per second. And all that will be divided by 4 times 10 to the negative third seconds. So when I do this, I get zero point zero 0.06 times 55. That gives me 3.3 kilograms meters per second divided by 4 times 10 to the negative 3 seconds. And that gives me 825 newtons is equal to the average force. Now, they ask you, what would this force be large enough to lift a 70 kilogram person? Well, weight is m times g, so that weight of a 70 kilogram person would be 70 kilograms times 9.80 meters per second, like that. Well, as you know, if you multiplied 70 times 10, you'd get 700. We're multiplying it by 9.8, which is even smaller than 10. So we're going to get a number smaller than 700. And the force we just calculated was 825 newtons. So the force that Roger Federer or whoever's hitting this 120 mile per hour tennis ball with, that force is well over the force required to lift a 70 kilogram person. I will say that basically, in case you don't understand what 70 kilograms is, I told my class that you could choose the person that was sort of the most petite person in the entirety of class, and they would probably be closer to weighing around 70 kilograms. And that's fairly reasonable. So just think in terms of that. You can also use 2.2. If you multiply 2.2 times 70, the 2 would get you 140. The zero point 0.2 would get you 14. So 154 is about the weight of a 70 kilogram person, roughly. So 154 pounds is pretty light, but still thinking of that as doing something with a racket overhead is pretty impressive that they're able to get that much force on it. Any questions on that? All right, let's jump to example 9.2. Example 9.2 says water leaves a hose at a rate of 1.5 kilograms per second with a speed of 20 meters per second and is aimed at the side of a car which stops it. That is, we ignore any splashback. So we're not imagining that the force of the car on the water is going to make the water back up at all. We're just going to allow it to hit, and then sort of surface cohesion is going to allow the water to just pour down the side or something like that. That's what we're shooting for here. What is the force exerted by the water on the car? So they want to know the force on the water due to the car. And remember, that's the wording we use. The first subscript is the thing being affected. The second subscript is the thing doing it. What we know is the initial velocity of the water is 20 meters per second. And what we also know is delta M over delta T. That's not a symbol that I've given anybody, but it says 1.5 kilograms per second. So it tells me that it would be smart to go ahead and call that 1.5 kilograms per second, call that delta M over delta T. Now, Newton's second law says the summation of the forces is equal to dp dt, and that gives us the summation of the forces is equal to uh, delta mv over delta t, which you can sort of treat as if it's a delta M over delta T times V. Now, there's a little more thought that needs to go into this, and I'm kind of inclined to let you guys read the example and think about exactly what thought goes into it. I think that's probably a better use of it, but I can tell you that this alone will give us the right answer, but it might not be satisfactory to you. And I'm glad, I'm happy that you're not happy with this explanation if you're not, okay? But watch what happens. Again, we're going on the assumption that, yeah, gravity's acting on water, air resistance is acting on water, but compared to the force that the car puts on the water, those forces are nothing. So this total force is the only force. So I can say now the force on the water due to the car is on the order of, and notice it would be in the opposite direction, so you could put a negative there, but I'm going to say it's 1.5 kilograms per second times 20 meters per second, which gives us 30 because 2 times 1.5 gives us 3, so 20 times 1.5 gives us 30. So that would be 30 newtons is roughly the force acting on the water by the car. That also means the car is experiencing a force of 30 newtons. Okay. Now, really, what's going on here is you can imagine the particles are hitting the side of the car, and then their final velocity is zero. That'll give you a little bit of a hint to get started on the other part of it. So I'm just going to leave this example here as that and go on to the next one and just tell you to uh, make this problem make sense by reading example 9-2. I'll just leave that as sort of an extra little bit because really that's what you're supposed to be doing the whole in every example in every chapter of every uh, physics class is really they give you an example and you're trying to make sense of how they did that, why they did that, what math was involved, all that good stuff. I need you to do the same thing every time you look at an example, not just the ones that I work. So I'm going to allow y'all to figure it out a little bit more. Now, with conservation of momentum, here's some equations that we're going to make use of. Is there anybody that can tell me under what conditions is linear momentum conserved? You can type it or you can just say it out loud. So
Um,
remember, go ahead.
when the net external force acting on it is zero.
Excellent. Good job. So yeah, under those conditions is when momentum is strictly conserved and only under those conditions. We'll learn something similar when we do conservation of linear momentum. So far, we've only learned conservation of mass and we've just sort of talked about that. And we've learned conservation of energy. That one we've actually done some stuff with. So good job on that. What I want to show you is if you imagine you have a particle of mass A moving with initial velocity VA, and then you have another particle of mass MB moving with velocity VB, then the initial momentum of the system is MAVA plus MBVB. Now, if you wait a little while, they'll collide like that, and then they'll separate, and you'll see this leaving with a velocity VA prime, a mass MA, and this particle leaving with a velocity VB prime with a mass MB. So P final is equal to MA VA prime plus MB VB prime. And conservation of momentum implies if the summation of forces is equal to 0, then P initial is equal to P final, and we get MAVA plus MBVB is equal to MAVA prime plus MBVB prime. And that is our idea of what we mean by conservation of momentum. Anybody have any questions on that? So just one quick example, example 9.3. It says a 10,000 kilogram railroad car A traveling at speed 8 meters per second strikes an identical car B at rest. If the cars lock together as a result of collision, what is their common speed afterward? So notice this one, there are forces acting. There's air resistance, but you can imagine air resistance on a train car that's 10,000 kilometers and moving 8 meters per second is going to be a pretty small force compared to, for instance, the weight of the train car, the normal force on the train car due to the tracks, the force that one train car puts on another. All those forces are way larger. And not only that, in terms of Newton's second law, you don't even count the force that car A puts on car B because that's an internal force. So what you can tell is, yeah, there's a weight acting down, but that normal force cancels that out. So the net force is essentially zero if you can ignore air resistance and just friction. So that seems pretty reasonable. Because of that, I can say P initial is equal to P final. And this is all one dimensional. So I don't need to worry about the vectorness of it. But P initial is going to be equal to the mass of the train car, which is 10,000 kilograms, times the velocity of the train car, which is 8.0 meters per second, plus the mass of the other train car, that's 10,000 kilograms, times the other train car's velocity, which is 0 meters per second. So this just gives us 80,000 kilograms meters per second is P initial. Afterwards, what we have is two train cars stuck together moving at some new velocity v final. So P final is equal to 20,000 kilograms times v final. So I can take 80,000 kilograms meters per second and set that equal to 20,000 kilograms times v final and solve for v final, and you'll get 4.0 meters per second. So that's how conservation of momentum works. Anybody have any questions on that one? All right. Well, I'd hope to do a few more examples by now, but that's okay. Remember, we will meet Wednesday. You do have potentially a day on Wednesday that you can take the face-to-face test too. Your face-to-face test too has to be done by Tuesday of next week. By 11:59 p.m. on Tuesday. I've given you via announcements and emails. I've told you how you can get it proctored by me via Zoom. I've also told you on what days, namely Wednesday, you can get it proctored by me in person by coming to the Virginia Beach campus. I gave you the day and the times. It might be JC 12, it might be JC 21, it might be JC 26. It could be any of the JC rooms, to be honest with you. So just keep an eye out for me. But you're also supposed to let me know by midnight tomorrow which proctoring you're going to use. In other words, are you using the testing center? And if so, what date and time? Are you using me via Zoom and what date and what time? Are you using me via Classroom and what date and what time? So make sure you let me know. You guys are free to go. Chat me your first and last name if you haven't already done so. But have a good one and thank you for coming, everybody.
Have a great night. Thank you.
You too. Thanks, Michelle.